Okay, so I would like to start for today's class into the Laplace transform. So Laplace transform, as you may see from my lecture before, the definition is to transform. Okay, to transform. So the idea is we are going to transform the function here ft into function of f. So that's the idea. So every time we have some function of t, we would like to transform that to another function we call the function of f. That's the idea. But the Laplace transform, to be precise, is going to transform differential equations into algebra. So you will get rid the order and then transform them into another form that it will be in the form or structure in algebraic. It can be maybe some polynomials or maybe something related to exponent. Okay. Now the Laplace we can define as in this integrations. So we are going to integrate from 0 to infinity e to the power of negative st f of t e. Okay. Now of course this is by means is the definition. So every time we transform something and we want to prove whether the transformation is true or not, then we are going to use this integration. And remember, the integration is lived on the dt. So we are going to integrate with respect to t. And if you remember, when we have this exponent, every time we do something with exponent, either the derivative or integration, we are going to have the result in its original form, right? It's still there. So that's why this definition is really can be really helpful, and we can have more useful transformation. Now let's see some examples of what we can do from here. Okay. So let's say we are going to Laplace transform just one. Okay. So we are going to transform, and we are going to use the integrations with e power negative st, and then this is the function is just a constant 1. Okay. And maybe to make it more clear, let me write adding terms limit, because we are going to take the integration with respect to the infinity, the endpoints infinity, right? So we are going to use the improper integral, if you remember the improper integral. Or maybe not t. T is our functions. Maybe b. Maybe better with b. Okay. And then e negative st and then dt. Okay. And then just take the integrations. We can take that as negative e negative st over s, right? S we treat as a constant because this is integration with respect to t. And then we take the I forgot the limit. This is from 0 to b. Okay. And then we plug in all the endpoints. So limit negative e negative sb, we substitute t for b, and then we substitute with 0, it's 1. Okay. But minus become plus 1, and then over s, and it's become 1 over s, because this limit is going to be 0, right? Maybe notes here. If you forget the limit, let me write here, or maybe let me write with more general
terms. Or maybe let me write a little bit left here. This is equal 1 over e to the x.
So every component in differential equation that is a constant, we are going to replace with 1 over s. So for example, if you have like plus 4 plus 2, then it will be 2 over s, 4 over s. Because 1 will be 1 over s.
So if we have, for example, Laplace 4, then this will be 4 over s. Or maybe another constant. Let's say c is a constant, so this will be c over s. C is constant. Okay, in the last maybe 5 or 10 minutes, I will deliver your midterm result. I just finished just 10 minutes before the class.
Yeah, I think most of you, in my opinion, really good job. Good job.
Okay, now let's see another expressions. Okay, let's see another expressions, and perhaps another expression is the Laplace of the exponent e with power of lambda t. So lambda is also a constant. So lambda is arbitrary or just a constant. Okay. And again, to prove this, we take our integral. Okay, we take our integral slowly. Write down the definition. Write down the function. And now because we have e, then we can maybe simplify the forms. Well, you could write limit for the infinity, but I will not focus on that because you're supposed to know, okay? So I will just write as it is, and then just focus on the inside functions that we will have s minus lambda and then t, okay? Yeah, minus my plus, okay? And then dt, okay? And then right here, you know what will we do now? We focus on this s minus lambda, s minus lambda t, okay, because t is our variable. To take this integration, I think we can use some substitutions. Let's say the u is our sub. So take u, and then we differentiate both sides, still there, and then this becomes dt, and then dt becomes negative 1 over s minus lambda du. And then we can replace dt from there. Then we multiply the constant, because s and lambda we treat as a constant, we can write outside the integrations. And then the inside is just e, u, and du, e with power of u and du. So it's just the exponent itself. So we could write e with power of u is just e negative s minus lambda t. This is from 0 to infinity. And then again, the same thing. We put all the endpoints, and when we put the infinity here, we take the limit, and then we are doing the same thing as the previous one. This will result in 0. Okay, this will result in 0. This will result 0 minus 1. Okay, because it's negative infinity, so 1 over e with power of infinity is 0, right? So we have this expression. Negative multiplied with negative, so we'll cancel this part here. So this will result in 1 over s minus lambda. And we can make a conclusion that the Laplace of the e with power of lambda t, where lambda is our constant, is equal 1 minus s minus lambda. So you can imagine if we substitute lambda with 2, 3, 4, and this will be s minus 4, s minus 2, 3, and 4. So Laplace transform, at the beginning, it takes some time to change function of t into function of x. The half part of the Laplace transform in the next section, we will do the inverse. We are going to inverse from the function of x to function of t. And why we need these two? Because sometimes when we simplify some solutions or simplify some differential equations, we are going to need these two techniques: transformation from t to s, and then get back from s to t. So why? Because when we are in the function of s, we can make all or most algebra operation easier. Like differential equations is difficult because they have the order, right? They have dy dx with the second derivative, third derivative. That's what makes the system difficult. But if we can transform all of the orders into algebra, then we can solve the equations by algebra operation. And then after we get the result, we're going to turn back into the function of t, the original one. Okay, so we have this. So if we take, for example, if we take Laplace of e, maybe 60, then this will be 1 over s minus 6. Okay. And then if we have a negative, for example, negative 3t, this will be 1 over, and now we have s plus 3. So we need to write that should be valid for every s that is greater than lambda. Okay. So constant, exponent, let's try the polynomials. Okay. We have t with power of something. Okay, let's take another page. Okay, maybe if you want to take notes first. Let me check. Okay, let's start from, maybe take the t first. Okay, t, I forgot the t. Let's take the Laplace transform for t. So we will have integrations e power negative st, and then multiply with t dt. And then how to solve this? We have e and t. We are going to take integration by parts, right? So we take t and e negative st. This will be this is integration, this is differentiation. This is negative e over s, negative st. This is 1. This is 0, and then we can take another 1. E s squared negative st. Okay. I think that's the result. Or if you want to stop just until this part, I think still okay. If we stop here until this part, then we are going to take the integrations as negative t e negative st over s from 0 to infinity plus 1 over s integrations e negative st dt. And this will result in, this will be another 1 over s, okay, 1 over s. This will be 0, this will be 0, and this will be 1 over s, multiply with, this is Laplace 1, right? It's 1 over s, so 1 over s squared. Or if you want to, just using the last part here, we can also do that. So another alternative integration by part, we can directly multiply this too. So we have this and minus e minus st over squared and this will be resulting minus 1 over s squared, and this will be the same 1 over s squared. Okay, let's imagine that this t can be powered with some constant. Okay? Let's say with n. Okay? Let's say with Laplace transform t with power of n. And n will be described as a constant and positive, so positive constant. So let's write down the definition for Laplace. Okay. And again, we did the integration by parts. Now we are having t with power of n. We have e negative st. This will be n, and then t n minus 1, and then negative e negative st over s. Okay, and then we stop here, and then take positive, negative, and the same thing. Negative t with power of n, e negative st over s from 0 to infinity, and then plus, okay, plus n over s is a constant, so let me put outside like this, and then 0, infinity, t n minus 1, and then e negative st dt. Okay. Now, any idea how we should proceed after it? How should we proceed? Any idea?
Okay, remember. Definition of Laplace always start with this e to the power of negative s. So whatever component beside this is a function of t. It's function of t. So the function will be t n minus 1. So this is actually what?
This is Laplace of t n minus 1, right?
So let's see, can we make some patterns if we, let's say, we try this and then make another one? Maybe we'll be making n minus 2. So let's just see.
And we can conclude from there. So first, from the above equations, we could write that Laplace t power n is equal n over s, and then Laplace of t n minus 1. Okay. And then if we take the Laplace of t n minus 1, this will equal, if we could imagine what it looks like, okay, this will have another n, another s, but it will have squared, and for n it will have another n minus 1. Okay. Because it will start from here actually, if you see from this part here.
If we take another derivative, it will go here and then this will be n minus 2. And it will reflect what we have, and if we take the Laplace of t n minus 1 is this, and make the same structure, and you will find that, okay, we'll have n minus 1, right?
Because we derive of n becomes those equations. And this will be Laplace of t n minus 2. Okay. So we could make some pattern here that when we have t power n, when we Laplace transform this, it will take the n factorial, okay, over some s with power of n, okay, and then Laplace of 1. Or we could simplify all of this, becomes Laplace n factorial over s power n plus 1, okay. And then we need to decide that s should be a positive number. So maybe an example on the right side here. So if you have a plus of the t squared, for example, this will be 2 factorial over s cubed, or this will be 2 over s cubed. If we have more, maybe 4. This will be 4 factorial, and then s with power of 5. So this will be 4 factorial is 24, right? And then s with power of 5. Okay, another notes for today will be the trigonometry. Okay, so trigonometry, also important Laplace. So let's take Laplace of the cosine, let's say cosine beta t. Well, should be sine with alpha, but I will just start with cosine. Beta is a constant. Okay. We could always start with the definitions in Laplace. Okay. And then we could take this into integration by parts. So take the e negative st and then cosine beta t. Now I will take this for derivative and this is for integrations. Well, you could switch this, but maybe a little bit different and take a while. I will take this because this is more easier to approach the structure. So we'll have negative s, e, negative st, and this will be becoming the sine beta t over b. You can take the multiply this too. So we will have e negative st sine beta t over b or over beta. This will be evaluated from 0 to infinity, and then plus, okay, because negative integrations, but I think we can factor out the constant. So factor out the s over beta, and then e negative st sine beta t dt. We could try to imagine if we take this into evaluations, this will result in 0. This will result in 0. Because the sine b t over b, if we multiply with t and t, if we take the limit, then this will be getting cancelled because they are, if we limit them, they will equal to 1. They are limit identity. If you don't remember calculus, and this will be equal to 1 and this will be equal to 0, so this will be 0. And the other one also, when we plug in 0, it's also 0. So this will be equal to the right part here. So let me write again, s over beta from 0 to infinity, e. Okay. And again, if we look carefully, this is the functions, okay, and of the Laplace transform, right? So we could write that this is actually Laplace of sine, because we could predict that the cosine and sine will both have the similar property. Okay? Because when we take the cosine, we will be getting sine, and if we take sine, it will be getting cosine. Okay, and take similar approach, okay, for this one. So take the integration by parts. This will be negative cosine beta t over beta. and this will be negative s e negative st. Okay. And we multiply of all of this, and we can write that the Laplace of sine will be negative 1 over beta e negative st cosine beta from 0 to infinity minus cosine beta t. Oh, I forgot the s over b. Let me write s over b here. S over beta, and this will be dt. Okay, and if we take some time to check our results, if we take the infinity, it will be 0. Okay, so we have negative 1 over beta. So we take infinity here, and then minus, and take 0 here. Okay. This part will be 0. Okay, the left part will be 0 because of the exponent. Because of the exponent. And you could also take some time to prove that when you have cosine over beta with the take limit, it's not 1 but it will be 0. It's calculus. We always keep it. So in short, this will be a 0. And this part will be, this is 1, right? 0 is 1, cosine 0 is 1. So we have positive 1 over beta. So we take the Laplace of sine is actually 1 over beta minus s over beta, and the whole thing here is the Laplace, another Laplace of cosine. Okay, now let's exchange all together. Okay, we have this sign, and we can exchange to the our equation at the beginning. So in conclusions, let me write here that the Laplace of the cosine beta t is equal s over beta, and this will be having a Laplace of sine. Okay, so let's exchange this, all this into this. So Laplace of cosine beta t is equal s over beta, and then take 1 over beta, multiply it, minus s over beta, and then this will be L, or Laplace of cosine beta t, okay, we solve this. Okay, we solve this. This will be s over beta squared minus s squared beta squared of Laplace okay. So we move out the s squared over beta squared plus of cosine beta t . I think my bracket is not good. Okay, and then plus the Laplace of cosine beta t is equal to s over beta squared. I think we can solve this, factorize the Laplace, and we have s squared over beta squared minus 1. Then this will be, we can simplify it. Okay, I will skip some part and make some conclusions, that this will be equal to s over s squared plus beta squared. So this is for cosine. And what about the sine? Sine we can exchange from here, if we take the cosine, remember that we have s over beta Laplace of sine. So Laplace of sine, we need to multiply with beta over s, with beta over s. So beta over s, so we are going to have beta over s squared plus beta squared.
Okay. So one last section within this detail is that Laplace transform is having a linear property. Linear property means it's like a derivative of integration, because it's basically an integral, right? So basically, when we take the integral for like some set of sort of equations that have like maybe a lot of components, plus something, we could Laplace transform and take Laplace on each component. Okay. Like in the integration. So we take integration, we maybe have x squared plus 2x. We take integration for x squared, we take integration for 2x, the same thing. Okay, any questions first? I think to understand how all this process works is basically the integration by parts. That's, I think, a must. That is the core principle on this Laplace transform. Most of them can be proven through the integration by parts. And of course, the other are some property in integration, like the improper integral, how to take that into the limit if we have the infinity. And of course, because we have limit, then we need to also consider limit property. Okay. So if we take, for example, if we take Laplace of some alpha function of t plus beta function g of t, we can say that we can have the alpha and then take Laplace of the f, and then plus beta and then take Laplace
and take Laplace of G. Okay. So we take this conclusion as the Laplace is a linear property. And also we could think this not in a definition that makes confusing, but this is actually, if we think on the basis of Laplace, this is alpha, and then this is just a normal integral. So because of Laplace is actually an integration, then it's also having a linear property. So what does that mean? So if we take some example, let's say we have a Laplace example of tan e with power of negative t minus 5t plus 8. Then this is actually, we can rewrite this and compute each Laplace for each component. Okay, this is step by step, but if you want to take direct approach and take all Laplace together, it's also okay, because I think it's not too complicated. Okay. But if you want to like really precise, you can take one by one, especially if the questions may be getting more and more complicated. So this will be tan s plus 3 minus 5 s squared plus 8 over s. Okay, so I would like to end up until here. Okay. We are going to have more examples to come, and some definitions for the existence of this Laplace. There will be no feedback for today's class, okay? So I think